connect my pen real quick. Pen doesn't connect. Yes, no, okay, cool. Okay, so today our topic is following. So we're going to talk about synchronization, and people who took or are taking my architecture class, they will see some similarities between these two lectures. However, this one will concentrate on slightly different subset of synchronization topics, right? So it will help you, both of them will help you. By the way, do you hear me well, right? Just wanted to make sure that we are good. Yeah, okay, thank you. Okay, so what is synchronization? So first of all, let's quickly understand how we are starting other CPUs, right? I mean, after all, remember, we always were talking about one CPU, but I was mentioning that, okay, scheduler is running on each CPU and stuff like that. The question is like, how do we start them? So inside main, there was this function, which is called start others. And this is the function which is responsible for waking up other CPUs. Remember, when we talked about booting a domain, we introduced this notion that one CPU is called a bootstrap processor, and other CPUs are kind of waiting. They're application processors, right? That's again terminology from Intel, and essentially BIOS kind of, BIOS wakes up this bootstrap processor, right? And this bootstrap processor is the one which was executing the bootloader. Then we loaded the kernel in memory, jumped into main, and essentially ended up running mp enter. Or maybe we ended up running actually mp main, right? This function, the very last. And this is where we enter the infinite scheduler loop, right? However, this function start others, what it does, it kind of like sends magical interrupts to other application processors, which are kind of like sitting idle. They're not executing anything. I mean, I don't know exactly the details of what's going on those CPUs, but from the point of view of application of operating system developer, they are not doing anything, right? And what we will be doing here, we will be, with each of these interrupts, we're going to send them a pointer to the stack, and the interrupt itself will send an entry point, essentially an address of a function, which has to start executing on this CPU when it is woken up by the interrupt, right? So okay, let's take a look at the start other. So what happens is that each CPU will start running some assembly sequence, right? And we can copy this assembly sequence anywhere in memory, but as long as it's not used. So x86 chooses 7000, right? It's the same address which is used by boot, which is guaranteed that it's not really used, right? And what we're going to be doing is we allocate a new stack. Remember, because the scheduler on each CPU requires a stack, right? So this is a kernel stack, which will be used by the main function or the mp enter functions on other CPUs, right? And set a magic interprocessor interrupt. Interprocessor interrupt is an interrupt which one CPU can trigger in such a manner that it's processed on another CPU, right? It's kind of convenient because sometimes operating system needs to synchronize actions across CPUs, and those interprocessor interrupts are a handy way of doing this, right? So, and this is also a mechanism which allows you to wake up other processors, right? So, okay, this is essentially the code of that start others function, right? So we say, look, let's convert physical to virtual, and this will be the virtual address of the code. So essentially, we just added 2 GB. We moved this. Remember, how we were creating the very first process. We're doing the same here. So essentially, there is a small binary sequence which is embedded in the kernel binary, right? And it has 2 labels: binary entry other start, binary entry other size, right? Entry other start is essentially entry other, meaning that entry point on another CPU, right? And we copy it into the code location, right? And then we're in a loop. We're gonna wake up n CPUs, right? And if the CPU is already started, we continue to the next iteration. If not, however, we say, look, we're gonna allocate a stack. And the question is like, where will you pass those additional arguments to the other CPU? How will you pass this stack? What the kernel is doing is saying the following. If this is where the code will be at 7C00, oh, pardon, 7000, right? Why not to pass 3 arguments right below here, right? -4, -8, and -12 bytes. We're gonna pass this stack, I mean, pointer to the top of the stack, so it's stack plus kernel size, pointer to the MP enter function. This is the function which the assembly sequence will start executing eventually, and a page table. Essentially, we will be using again this handicapped page table, which contains only 2 entries and uses 4 megabyte pages. Remember, we use this during booting, and each CPU will kind of go through a boot sequence, but it will be a little bit shorter. And then you say, look, we'll use the advanced programmable interrupt controller to send this magical interrupt, right? I don't go into those details, how interrupt is sent. You will see it if anything, but this is essentially the entry point, entry other. It's the first assembly instruction which start executing on the other CPU, right? So it has, first of all, clear interrupt flag, meaning it disables interrupt, and then, you know, put 0 in the AX register, put zeros in all these segment registers, right? Then load the global descriptor table. We were using the same, right? It's memory is cache coherent, and we're going to talk a little bit about it today, what it means, cache coherence, right? Then we say, look, please like enable segmentation, then do a long jump to, again, the CPU wakes up in 16-bit mode of execution, right? So we're gonna put the CPU back into 32-bit mode of execution, start executing this start 32, and what we're gonna be doing here is, again, since we are using the 4 megabyte pages, turn on the 4 megabyte page extension, use page dir as our initial page table. Remember, it's right under start. So start is a label, and linker knows where it is, so it's at 7000, right? So start -12 is right where we place this. We place 3 arguments here, and this is the entry page dir, right? We load it inside the tier 3 register and load the paging, start the paging, essentially read control register 0, set up the paging flags in the EAX register, and load EAX back into control register 0, right? Now we are switching to the stack allocated by start others. So the stack itself is a start -4, and we're calling the MP enter function, right? Since now we have a stack, we can really call, it's an indirect call, meaning that we are calling a function pointer. Again, this is a 7000. This is our start label, right? And this is where we pass 3 arguments. So this is the page table entry, page directory. This one is pointer to the MP enter function, right? And this third one is apparently a stack, SP, right? Got it? Okay, and after that, the CPU is running inside MP enter function. MP enter function creates a kernel page table, initializes interrupt segments and interrupts, and essentially at some point, let me just spend a little bit of time here in the seginit function. So remember I told you that each CPU will have its own global descriptor table, right? This is how we get the instance, right? Remember, we have an array of CPU data structures. We can query the advanced programmable interrupt controller to get the CPU ID, right? And we use the CPU ID as an index into the array. Maybe it's CPU number 2. This is 0, this is 1, and this is 2, right? And here we initialize this global descriptor table, which is private to the specific CPU, and we load it into this GDT into the local instance of the LGDTR register on this specific CPU, right? And if I ask you a question, so why do we really need a different different global descriptor table on each CPU? It's a tricky question. I mean, you have to follow really, really closely to understand what's going on and why we need it. But you can answer this question, so maybe someone can guess.
When one of the CPU is interrupted, it needs to change the code segment. And if we are using, all of them are using the same, then it might cause an issue.
But look, this is the code segments right here. So this is the kernel code segment, and this is a user code segment. They are identical on each CPU, right? So there is nothing like CPU ID here or anything, right? So we are setting kernel code segment as executable and read-only, starting from 0, spanning the entire idle space, requiring the CPL 0 to access, right? And the user code is similar, executable, read-only, starts from 0, goes to the end of the address space, requires CPL 3, right? So code segments are the same, looks like. But what is different? Essentially, I'm digging for this answer. So I'm trying to figure out, why do we need a separate global descriptor table on each CPU? Why do we need like something private per CPU? Anyone? It's a little involved, but you can guess. Another thing is to assign it as homework, right? Then you can, or my final exam. So why? Anyone else? Remember the interrupt transition. So imagine a picture of two CPUs. This is the GDT on one of them, and this is the GDT on another, right? So one CPU, another CPU. CPU internally has a register which points to the GDT, right? What happens during the interrupt transition? Imagine process 1 is running here. Process 2 is running here. Each of them will have their own page table, right? Those will be different. And the CR3 register will be pointing to two different instances of the page table. Agree with this? And this is I forgot the register which holds the GDTR, right? GDTR, and this is GDTR register, right? So this address space obviously maps this process. It has a user stack. This one also has a user stack, right? Can anyone guess from here why we need separate global descriptor table?
The stack segment changes.
Stack segment. Stack segment, look, we created this, remember, we're always using either U data or kernel data as a, like, it seems that these 4 entries, which we just seen, even 5, the 5th one is just 0, are identical on each CPU, right? That's what we observed from previous page. So this is this kernel code, kernel data, user code, and the user data. They're the same. They're here as well. Kernel code, they're identical. Nothing is special about them. Kernel data, user code, and user data, right? There's yet another field here, which I didn't talk much about it. Yet another entry. Which entry is that?
TSS.
TSS, exactly. So why do we need separate TSS? Who can guess?
Because the kernel stack is per process.
Exactly, because the kernel stack is per process, and TSS on one CPU will be pointing to one kernel stack, case stack of this process P1, and on this one, it will be pointing to the kernel stack of P2, right? That's the whole point. Why? Because the timer might happen almost at the same time, right? So, and these, both of them got preempted, and like on two different CPUs, these two different pages, maybe it's a timer interrupt here, and maybe it's a page hold here, or maybe it's a syscall here, right? So this page is different and it's per process. Do you understand this? And that's why when we switch from one process to another on each CPU, we'll be reloading this entry in the TSS, essentially the pointer. Everything will stay the same because we don't have to change the kernel segment, kernel code, kernel data, user code, user data. They are all identical, starting from 0, going to 4 GB, right? But the TSS and the TSS instance doesn't need to change from process to process, but this entry, this field which points to the stack, that has to change, right? Do you understand this now? And that's why it's per process. Okay, that's important to understand. Like, it's a subtle detail, but I mean, like, since we covered everything in that level of detail, and I want you to be able to like code your own operating system kernel tomorrow if someone asks and make money, for example, right? You can do this, right? So okay, glad we understand it. Okay, so we have array of CPUs. x86 used to do per CPU variables in a slightly more elegant manner. And they changed it. Like, it used to be that per CPU variables on each CPU, like all the per CPU variables were offset with something like GS segment, right? So base of the base of the GS segment was different, right? And which means that you could address on one CPU GS0 would land here, and on another CPU GS0, would land on this address, right? Because this is the base is different. So GS was the only segment in x86 which was which differed from one CPU to another, right? They changed it, and now they just use an array of CPUs, right? And use the CPU ID instruction, right? But this is like essentially per CPU data structure. So this contains the state of each CPU, right? And we kind of familiar, right? Each CPU will have a scheduler, and when we context switch away from the scheduler, this variable remembers specifically the context which sits on the top of the kernel stack on which the scheduler is running on each specific CPU. And that's why we have a GDT here as well, right? And that's why TSS is here as well, task state, right? And essentially, this is the only field which we're changing on each CPU, right? The flag, whether the CPU has started, that's how many times this will become clear today, later today. We invoke the push CLI. So essentially, it's kind of like make sure that we do not restore interrupts or re-enable interrupts sooner than we need, right? And the current running process on this CPU, right? Okay, so CPU ID is effectively a function. It queries the advanced programmable interrupt controller, returns a number. Maybe it's too low level, we don't really care. But the problem is that on every CPU, remember, we started running MP enter. On the first one, we ran main. On all other, we ran MP enter, right? And this MP enter, hold on, MP enter, maybe I'm wrong. MP main, we started running on all CPUs. MP main, right? This is the function, MP main. And it printed this string. No, hold on. MP enter, I guess, code MP main, right? And I apologize for that, so I forgot. Right, so MP enter, this is what we started running. It calls MP main. And then MP main ends up entering the scheduler, and the scheduler essentially looks at the global variable. They access this variable under a lock, right? So only one of them access it at a single unit of time, but they all go through this global table of processes, pick the process to run, and essentially schedule it and run on a CPU, right? Is this clear? That we have a scheduler per CPU, and so multiple processes can run at the same time in the system, one process per CPU, right? And then we context switch on each CPU as well, right? All good? Okay, now there's this question. Unless you took an architecture class, it might be a little bit mysterious to you, because you say, look, I understand that there are CPUs, yet at the same time, it seems that they access the same memory, right? Because CPUs are executing their own code, and maybe all of them try to move something to or from an address, right? And maybe it's the same address. So how is the conflict? How this conflict is resolved? Who can tell me? Like maybe it's an address, same address. One moves from an address, another moves into an address, right? This one also moves from an address. How do the CPUs share the memory in such a manner that they don't have a conflict? Do you remember?
They have a write back thing, I believe. Like so. So one thing is that there is something called, I believe, I remember something learning about cache coherency, where multiple CPUs will have some kind of a protocol that they talk when they kind of like write to a single location.
Exactly. So let's quickly take a look at this protocol. And I forgot that I have to open like a separate, or I have Turkey on my look. Let me quickly, there must be Office 365. Unfortunately, I log in only once a year into this, and I just quickly figure it out. Just to run PowerPoint, I will start Office 365. Do I have it here? Yeah, this one. This is a good way to log in. It's just that this part of the lecture is done in PowerPoint. So let me just quickly play PowerPoint login here. I should have prepared. Hopefully this will work. So let me push. And just quickly take a look at the cache coherence, right? Stay sending, whatever, sure. Outlook, we don't need any Outlook here. We'll just go to PowerPoint. Yes, no, doesn't work. No, it didn't work. Actually, I wanted this lecture. Okay, good. You see the screen, right? With the PowerPoint slides, which are still loading, but will be there in a second, right? Intel memory hierarchy. Yeah, it's on the screen.
Yeah.
Yes. Actually, so now the pen doesn't work with this. Goodness. Pen. I can highlight, but I can only use. Oh no, I can actually. Cool. Although it's very slow, but maybe Control Z works. Okay, look. So let's understand one more time, what is a processor, what is a core, what is a PCI bus, right? So when you buy a processor, it will come with multiple cores, right? So each core will have its set of registers here, right? We'll have a private L1 and private L1 data and L1 instruction caches, right? And it will be unified, but still private to the core L2 instruction and data cache, right? Then if we buy a processor, right, it will have multiple cores, and the whole thing, the whole processor, which I mean, this is the thing which you usually get from the store, right? You can't just buy a core, right? It's the whole processor. We'll have a unified shared L3 cache, and this shared L3 cache will have a couple of controllers. One memory controller will connect this processor to memory, and there will be some local memory, local to this CPU, right? It will connect it to a local PCI controller, and you will be able to connect to local PCI devices here, right? Let me just dig up the chart. And then if you on a server grade machine, you'll have multiple processors, right? And this picture, again, try to clear everything. I don't know how to do this, right? So essentially, the second processor will be absolutely identical. It will have its own couple of cores here, right? 1 and 2. They will have private registers, private L1 caches, private L2 caches, right? A unified L3 cache, again, memory controller, which connects to another chunk of memory, right? So you might think of it like, look, hold on, like this is like maybe this is 64 GBs of DRAM. I'm sorry for this handwriting because this is how it works here. And this one, another 64 GBs of DRAM, and the total capacity of the machine is 128 GBs, right? So it's quite common to have those when you have multi-processor machines, they will have their own memory controllers, right? Private to them. So it's truly a distributed system, right? And this QPI link is what connects these two packages, right? So allowing you to send messages back and forth at a high speed, right? And if you need to access remote memory, so for example, from here, you want to access this memory, right? Then the messages are sent over this quick pass interconnect link, right? So I was mentioning that before, right? It's just a recap. Okay, now what happens when one core tries to load a cache line, right? In all transactions with memory, between memory and the core, and between the caches and the core, happen in the unit of cache lines. And on Intel, the cache line is 64 bytes. On AMD is the same, right? But it's just, again, it's a design choice. You can choose different cache line sizes. Apparently, it works quite well, right? So no one's trying to move away from this size right now. Okay, so to load something, right, from registers, roughly speaking, it takes 0 cycles. I mean, people who took the architecture class, they understand that what it really means, like kernel, like the pipeline was bypassing, that what it means to really access registers and stuff like that, right? But in our terms, let's just think that it will take you can read the registers and execute an instruction in the same cycle, although in practice, it might take you a couple of cycles internally on the pipeline, right? So imagine we do load, right? How many cycles do you think it will take you to access the first level cache? And people, again, who took my architecture class should know quite well, but I will ask everyone.
I think a cycle or two.
A few cycles.
A few cycles.
2 to 3 cycles, right? So absolutely, right? But what happens is that if you're missing L1 cache, right? Essentially, if the cache line which you're trying to access is not there, the L1 cache forwards the request to L2 cache, right? L2 cache might not have it either. It will forward it to L3 cache. L3 cache is running something what is called a directory. It knows which memory is responsible for containing this cache line, and the request is routed to memory. And at this point, the memory replies with this blue cache line, and the blue cache line, since on Intel up until very recent years, the caches were inclusive. So if you bring the cache line into L1, it's also will be brought into L2 and L3, right? So this blue cache line, and it's some address, or physically you're reading, you said move of some address. And I'm again apologizing for the handwriting here, right? Imagine the same address is now accessed from another core. You can think of the following. You may think, okay, maybe caches can play some kind of protocol in such a manner that there will maybe multiple readers who read the same cache line, but there will be always only one writer, right? Because updates should be unique, right? So, okay, you load the cache line here. Again, it's not an L1, it's not an L2. Request goes to L3. The cache line is in the shared L3, right? Which means that L3 replies with this cache line, and this cache line gets populated in the L1 and L2 caches of another core, right? Right now, if you read this cache line again on this core 0, you will hit L1 and everything will be just fine, like few cycles, and that's about it, right? Now let's take a look at what happens if one of these cores tries to write a cache line. This is where this cache coherence starts working underneath, right? It's a protocol which it ensures that there can be multiple readers, but there will be always only one writer to the cache line. So imagine this core tries to store, core 0 tries to store an address, right? Store something into the same cache line. It might be 1 byte or might be like the whole cache line, right? As long as it fits in the cache line, right? So I draw this updates with orange light. It asks the cache, okay, do you have a cache line? The cache says, yes, I do have the cache line, but it's actually in a shared state, which means that the cache line is also, it may exist in caches of other cores, right? So it's not okay to write this cache line. What we have to do is we first have to evict this cache line from other cores, right? And so it sends the request down the line to L2 and L3. L3 again has the directory. It goes up into those caches and invalidates those cache lines, making sure that no further reads will be allowed. So essentially, those cache lines disappear from those caches, right? And the cache line stays only in the exclusive state on this L1 cache of this core 0, right? At this point, this core 0 can write the cache line multiple times. It can read and write, right? But it's essentially, you can imagine that if the core 1 will try to load this cache line again, what will happen? It will go down to L1, go down to L2, go down to L3, L3, which keeps track, it's the directory protocol, it keeps track of where the cache line is in a caching hierarchy. It can be anywhere on this machine, right? But it knows, it goes up here and says, okay, hold on. At this point, you have to write this line back to memory to make sure that the most recent value will be in memory. And it's like, it can differ between like different coherence protocols, but let's imagine it happens in this one. And at this point, the cache line is again in a shared state on this core 1, right? So essentially, this is a distributed protocol which is played at the level of caches, which ensures that only one core can write a cache line. If the cache line exists in any of the caches, it first gets invalidated. The core loses access to this cache line, and one core which tries to write gains exclusive access. Is that clear? That's essentially a 2-minute primer on cache coherence. Any questions about it? Everyone is good?
Yeah. I just got confused. Like this is the processor and like this is processor 1. Mm-hmm. As in like L3 shared across cores, right?
Yeah. Okay. Yeah, but what is the question? L3 is shared across cores. There is a little bit of like
I just got confused. Like I was thinking with L3 shared, both of the processors should have the same L3 is what I was thinking.
No,
but
it's different. So L3 is actual silicon, so it's like actual gates which implement L3. Those two guys are different. And if you want something from L3 of another core, you will have to send a message across this QPI link and get it from here. And it will take you some number of cycles, and we'll just go quickly over those cycles real quick in a second, right? And this, it will send a message back. So think of it as a network, and it's a distributed system. It keeps track of where the cache line is. It might be here, right? So maybe when if you do the store here again, you actually have to go both here and up here and invalidate those cache lines, making sure that no core in a system has the cache line in shared state or exclusive state, right? Does it help?
Yeah, got it. I've just got confused that if these two are cores or processors.
Yeah, so these are cores. You typically buy like 4-core CPU with each core running 2 hyperthreads, something like that on Intel on the desktop or laptop grade machine, right? On a server, there will be like something like 20 cores, and you will be running 2 threads on each, so 40 threads across the processor. If you have a dual processor machine, the total number of logical execution threads will be 80, right? So on Linux, it will show up as 80-core machine. In practice, it's like 40 cores, but two hyper threads on each core. Hyper threads will share the they will have their own private logical registers, like EAX will, of course, will have a copy of EAX here and a copy of EAX here, but in practice, there will be one physical pool of registers, right? And again, they will be renamed as during the instruction renaming stage, but they will share L1 and they will be sharing L1 instruction and data caches between two hyper threads. They will share, of course, this cache, and of course, all cores will share shared L3 cache, right?
One more question. The L1 data and L1 instruction, right? Like, how does the CPU know what is, like, is it from the data, is it from the data segment and code segment registers that we put in?
Not really. So it fetches instructions from the instruction pointer. So everything what is fetched from the instruction pointer will be cached in this instruction cache.
Okay, got it.
And everything what is shared. The question is like, what happens if you start fetching? Actually, I don't know. I should have asked this question myself. What if you're moving or like reading or writing instruction streams? So essentially, if you're saying, I don't know, you probably will invalidate the entry in L1 instruction cache, get it in the L1 data cache, do a write, and then when the instruction will be fetched again, it will be refetched into the L1 instruction cache.
Okay.
Good?
Yeah, got it then.
Okay, let's quickly go through numbers. So we said that accessing L1 is roughly 4 cycles. How many cycles accessing L2? And the size of L1 is, each of these are 32 kilobytes. So it's 32 for data, 32 kilobytes for instruction, right? So just to keep track of sizes. How long it will take you to access L2?
Ten cycles?
Around 10 cycles, right? So that's not bad, not a bad guess. 12 cycles. The size can be around 256 kilobytes. How long it will take you to access L3? Any guesses? Well, there is this law that latency is the square root of capacity. So roughly 35 in this machine, 50 cycles, right? But the last level cache can be up to 30 megabytes, right? So quite a giant cache, to be honest. As I was saying, my first machine, which I got, had only 8 megabytes of DRAM, and now the caches are 30 megabytes. It's kind of unbelievable. So how long it will take you to access local memory? This one. The memory which is local to you. Yeah, 200 to 300 cycles, exactly. And the memory can go up to terabytes, right? You can buy a stock Dell machine which has 96 DIMM slots. And a couple of years ago, the max DIMM size was 128 megabytes. Maybe it went up actually these days, right? So plus if you have non-volatile memory like Intel Optane, right, then you have a bunch of non-volatile memory up to like multiply by 10. If I ask you a question, how long it will take you this cache? Imagine the cache line is actually right here, and your pass, you're asking L3, but L3 has to go and get the cache line from here. It also takes you some time, right? And it takes you 122 cycles. So it's kind of longer, to be honest. Go here, even a little bit longer, 132 cycles on this machine. If you go across the QPI link, this one, right? And the cache line is in a last level cache, but on another processor. It will take you roughly what? No one knows, I don't remember myself, but it adds 120 cycles approximately, right? Oh, wait, where's the number? We don't have a number. Disappeared. Okay, so accessing remote memory, right? Local memory was 241 cycle. If you go to the remote memory, it takes you 365 cycles. So clearly local memory is better. If you really like running some latency sensitive applications, make sure that the CPU runs the thread which accesses the memory, which is local to this processor, right? So people started doing these optimizations these days, right? although typically it's hidden for input. So this link roughly takes 150 cycles, right? And so if you're going to L2 here, I don't know if you can see it on my screen because I have a chart here. Let's just move the chart somewhere where we can move the chart, for example, here, right? 272 cycles. If you go up this stack, 282 again, slightly because you have to go up to yet another cache, right? And if you go over the PCI bus, it roughly takes 600 nanoseconds. I take this number from this paper, which is DCE Express, right? And it roughly translates to 1500 cycles, right? Which is like, you can understand, like now you know the numbers. So, I mean, obviously this PCI device might not reply that fast because if it takes it forever to process the packet which you send, then yes, but typically like you can send a packet from two servers which are connected back to back with an optical cable. It will take you less than a microsecond, so less than 2000 cycles, right? So that's not bad. Right, so now we kind of understand all the latency. We understand cache coherence, right? So we can go back to the synchronization lecture. Are we good now? We understand how the hardware works. Any questions about it? Good. Okay, let me quit this. I have a couple of slides here, but let's just for the sake of saving time, let's get back here. Okay. So what is synchronization now? Imagine a disk driver maintains a list of outstanding requests. And each process can add requests to the list with a system call, for example, right? And those processes are executing on multiple CPUs. Imagine we have a very simple list data structure, which contains the integer element and the pointer to the next element of the list. So literally it looks like this. Like this will have maybe 5, this will have 17, this will have 22, and so on, right? And this is the insertion function. You can take a look at it, and we'll take a look at a little bit later. So there is a global list variable, right? And to write into this variable, if you're writing from two different CPUs, you will use this cache coherence, which bounces the cache lines between the cores, right? Okay, so to insert an element into the list, what you're doing, you're allocating a new element with the malloc. You have an L, which points to this element, right? Right here. Then you write some data saying, okay, this will be 5. Then you say L next will be containing the pointer, which used to be contained by the list. And list itself will contain now the pointer to this element, which we just allocated, right? So inserted into the head of the list, right? So very simple. Now imagine what happens when two CPUs access the same list, right? Now we have a problem. One processor, which runs one, like process 1, P1, which executes a system call maybe, allocates a new element with a malloc system, with a malloc call, right? Another does the same. It also allocates an instance. You write some data, right? And both of them reach the line which they first write data 5, and maybe here it's 17. And now they reach the line which updates all of them to like update their pointers to point to the current element pointed by the list variable, right? And at this point, one of them gets ahead, like wins the game on a cache coherence protocol. Like essentially the cache line, it says, I want to write into the cache line, and the cache line is migrated like in exclusive state to this core. And it updates the global list variable, right? And then the other guy, which was just behind, says, okay, look, now I want exclusive access to the cache line, which contains this list variable, right? So the cache line moves over here, and this guy does the write, right? As a result of it, what just happened? Who can tell me? We lost one element on the list. This element, although we kind of ran through the same code, we were trying to insert it, but this element A is not on the list. B is on the list, right? Because we will traverse it like that, but A cannot be reached, right? So we lost an element, kind of leaked memory or leaked some data, and we'll never recover it, right? Agree with this? Do you understand how it happened? Now the question is, we want to implement something what is called mutual exclusion, meaning that only one CPU can update the list at any given moment of time. We say, okay, look, we will say that the code, which is marked green here, is a critical section, and we will acquire some kind of a lock on the special lock variable, which is over here. And if other CPUs are trying to enter the same sequence of code, they will be blocked, waiting here, waiting for this process to finish and release the lock, right? And at this point, the other guy can acquire the lock, enter the critical section, right? Then each CPU will execute, only one CPU will execute this sequence at a time, right? Which means only one of them will compete for this cache line, which contains the global list variable. Only one will do the update, and then the other will take a turn, right? So, I mean, it's not a big surprise to you because you all programmed parallel systems, right? So you know how it works, right? Our goal today is to understand how these locks are implemented, what's inside this acquire, right? And a couple of other synchronization primitives, right? But do you agree that this mutual exclusion and critical sections will solve the problem if only we can build this acquire primitive? Yes or no? Any questions again? All good? Everyone agrees, say yes. So how can we implement this acquire primitive, which acquires a lock, right? We can build something what is called a spin lock, right? So inside acquire, we pass a data structure which has a field. LK is this data structure, has a field locked or not. If we're gonna spin until it's unlocked or this locked turns to 0, right? So it's an infinite loop. We check if it's 0, we write 1 into it and then break out of the loop, entering the critical section. If it's, however, 1, it means that some other processor already acquired the lock and we will be waiting, spinning on the lock, right? And at some point that other processor will flip this value back to 0, right? From 1 to 0 again, right? And then we will enter. Agree with this? My question is the following. Do you think this implementation of this acquire primitive is correct or not? People who took my architecture class, that should be fresh in their memory. No. Okay, tell us why.
Is it because like it can translate into a couple of assembly instructions, and we might check in a register that it is 0, and then there might be an interrupt or something like that. And
not even an interrupt, but look, two threads of execution, 2 CPUs can reach line 25, this line at about the same time. They both will see that this is 0, right? It's not locked. The cache line will be brought up in their caches. It will contain zeros, right? Both cache lines will be in a shared state. Both of them can read this cache line. Agree with this? After that, they say, look, there will be some branch instruction, and they go into this branch, and essentially both of them will be write 1. One of them will win the race and will write switching this cache line from 0 to 1. Then another one, this cache line will be migrated here. It will already contain 1. This guy will overwrite it was 1, but it doesn't know that it was overwritten was 1, right? And both of them will break from this loop and enter the critical section, and the list will be broken again, right? The problem is that this check and this update are not atomic, right? So these are 2 different instructions and 2 different operations on the cache line. One reads it, and meanwhile, while you read the cache line, this cache line can be evicted, written by another CPU or whatever, right? Agree with this? So we need to make this operation atomic. And there is an atomic primitive on Intel machines, which allows you to essentially swap the value in memory with a new value while returning the old value. It's called an exchange instruction, right? So what happens here is the following. We're using this exchange instruction in this infinite while loop. We're always writing 1, and we're seeing what this exchange instruction returns. If it returns not 0, then it means that there was the old value was 1. We tried to write 1 again, but the lock was locked. But once we see 0, it means the cache line was actually 0, which means we were the ones who actually wrote 1 into it, right? So we got 0, which means that we are the only ones. This CPU is the only one CPU which acquires this lock, right? Which switches it from 0 to 1. Is it clear to you, this intuition? Do you see how this exchange works? So there was a cache line, maybe it's 1, you write another 1, but you get back, this exchange returns the old value, and it will return back to 1. If another CPU, and you're doing this in the loop while well, you're still seeing not zero, right? But at some point, someone else says, okay, I want to write this cache line. I want to write 0 here, another core. This cache line gets evicted from here. So it goes from shared state to invalid, right? It migrates here. Here it becomes in the exclusive state. The 0 gets here, right? And you do another iteration of this loop. You again switch this cache line from exclusive to shared. You get the cache line actually in the exclusive state. So it will not be shared. It will be invalid here. So you get your cache line in the exclusive state. You write, it contains 0 here. You write 1 again, and you get back, however, not 1, but you get 0, right? And then you essentially say, oh, got it. I got this 1, and I will exit from the loop, right? Agree? I got 0, I mean. Clear, or any questions about it? So, okay. How we implement this exchange instruction? It's an assembly instruction. So exchange is a function. In some machines, you might have a compiler intrinsic, which does this. x86 does it by hand to just illustrate. This log prefix is important. Without this log prefix, the exchange operation is not atomic because it will be split into micro operations. And one will do a load and another will do a store, and it's not guaranteed that the cache line will stay in the local cache. When you say log the cache line, it guarantees that the cache line will not be evicted. Even if you see in an eviction request, the cache will delay responding to this request until this instruction finishes completely, right? Which means that the cache line will be logged logged to this specific local cache, right? And essentially, this is the syntax for the inline assembly. So it just takes arguments and just uses this assembly instruction, right? Okay, so far so good. We have this exchange primitive. Unfortunately, this is not yet again correct. So even with this atomic exchange instruction with a log prefix, the compiler itself might reorder instructions up and down the instruction stream, right? That's why it's important to also tell the compiler, it's a compiler directive says, okay, please do not move instruction, because if this acquire function is inline, right, in your code, and you have something like log and exchange, right, maybe there are some move operations here, right, which update something, and compiler says, okay, exchange operates on one cache line, like on A, for example, move operates on B and C, and there is no real reason not to reorder this instruction. Supposedly, it's a correct transformation, right? You would put this move instructions above the log, and in terms of equivalence, the code looks equivalent, right? That's why ideally you should say, okay, please do not reorder, like at compile time, do not reorder instructions around this point, right? So everything what is after this will not be moved forward. Although typically compilers don't reorder around the log instruction. So even if you forget this synchronize, typically it just works, right? But still, nevertheless, make sure that you know this directive, you know what it means, and make sure that the compilers don't do that underneath, right? Okay, so we're good. We understood what spin locks are. We understood how to build a critical section to make sure that we provide mutual exclusion for this list updates, and only one thread can execute those 3 magical instructions, which essentially update the list pointer and the global list pointer and the local next variable, right? Agree? Now let's take a look at the problem of deadlocks. Imagine the following sequence. You say you have 2 logs, and one processor acquires a log A, another log acquires log B. And imagine this later on, you say, look, this first guy tries to acquire B, which means that it will be waiting for B to be 0, right? But B is already 1. And since this guy tries to acquire 1, there is kind of like this dependency between them, which essentially results in a deadlock. This both pieces of code will forever get stuck in this infinite loop. Do you see what's going on here? This is called a deadlock. So what do you think is the solution to the deadlock? how to avoid it. If I would ask you to write a code which avoids the deadlock, what would you do? There's a simple rule of thumb. Always acquire locks in the same order. So if you acquire them A and then B on this, in this sequence of code, always acquire A and then B, right? And you say, okay, this is kind of naive, right? And it's so trivial. Why is it even like anything what's worth mentioning? But imagine you have some kind of a graph of objects, right? And they're somehow connected. And you say, look, I know that I have to build some kind of an atomic transaction which locks objects A, B, and C, maybe only just these three. And maybe you enter this on like it's on CPU one, P1, and maybe another CPU, and I will change the color here just to make it a little bit more explicit. Tries to build a transaction which also touches three elements. Maybe it's D, B, and C as well, right? The point is that those two guys have to acquire locks in the same order. So one of them has to acquire ABC and another has to acquire DBC, right? Right? Or maybe BCD if the order is such, right? And so how you do that? So essentially you first determine the set of locks which you have to acquire, and then you sort them. So for example, in this example, you can, I mean, how can you sort? Maybe you can use an address of a lock itself, because all of them are in memory, and you just sort them to make sure that you go from locks, from the log data structures, which from lower to higher address, right? This means, for example, one will be acquiring A, B, C, and another will be acquiring B, C, and D, right? And then if D participates in some other transaction, so for example, maybe it's D, A, and D, A, and B, then again, the transaction will be something like A, B, and D, right? That's the correct order of acquiring the locks. That's to avoid the deadlock. Otherwise, there is a possibility that you can arrive to the same situation which you have with locks A and B, and will be waiting in a deadlock, right? So is it clear? No, not clear? No is a previous answer. Okay, everyone knows about the deadlocks, maybe, like everyone took the parallel programming class. It's good. So yeah, locks have to be acquired in the same order. In an operating system kernel, there is yet another unusual way how you can arrive to a deadlock. Imagine you acquired a lock. Imagine you processing a network packet interrupt. And inside this interrupt handler, you say, look, I will insert something on the list, right? And which means that I will acquire a lock A. And it's like you acquired lock A, just about to insert something on a list, and another interrupt arrives. And you start processing again the interrupt handler. You get to the same network packet function. You try to insert yet another packet into the list, right? Which means that you try to acquire the lock again. And again, you have this dependency that you already acquired this lock before, which means that you're deadlocked, right? So what's the solution in this case? How can you avoid deadlocks in face of interrupts? Disable interrupts, right? Exactly. So which means never hold a lock with interrupts enabled, right? And this is what x86 is doing. So essentially inside the acquire function, it first uses the push CLI, it disables the interrupts, right? But since you can, like maybe you're acquire A, which disable the interrupt, then you do acquire B, which also disables the interrupt, but then you release B, right? If you simply like do push CLI and pop CLI and inside the release function, you will re-enable interrupts here while the lock A is still acquired, right? That's why you have to count how many times you really pushed or disabled interrupts, right? Like, so if you disable it once here, another here, the counter will be 2, here it will drop to 1, but you will not yet release the, like, you will not yet re-enable interrupts. What you will do is that you will wait until you get the release function over here, right? Then it drops to 0, and this is that at this point you re-enable the interrupts again, right? Are these logs that you can acquire multiple? Are there logs that you can acquire multiple times? No, you acquire one log at a time because you switch from 0 to 1. But imagine you have logs like A, B, and C, right? So different logs. Any other questions? Okay, so let's take a look at this push CLI real quick. So push CLI uses a counter, right? So the first time it essentially reads the eFlags register, right? Does the CLI. If the counter itself was 0, which means that we acquired the interrupts the very first time, maybe acquired the log the very first time, maybe interrupts were already disabled. Like you entered the interrupt handler and you say, look, I want the interrupts to be disabled altogether, right? You might think of, okay, what's going on? Like, yeah, so in this case, you don't really have to re-enable the interrupts, right? And that's what you're doing here. So you essentially say, look, I will check the eFlags registers, and if the interrupt flag is set, I will save that in this variable on this CPU. Remember, there was this interrupts enabled flag, right? Or field, right? And then you say +1 to this number of CLIs variable, right? So it works kind of like a stack, right? And pop CLI is the same. So if your counter is greater than 0, if it's negative, you panic, right? If it's equals to 0 and you have to re-enable interrupts, you do re-enable them by setting the interrupt flag in the flags registers. However, if this one is 1, you just don't go here. If the interrupts were not enabled to begin on, you also skip this instruction, right? So this is how push CLI and pop CLI work, right? Clear now? Now, there is yet another interesting problem here. So imagine you want to implement a send and receive queue, right? It just sends one pointer between two CPUs. So the code is like that. So you have a queue has a pointer to some object which you want to send, right? Your send function, what it does is it says, okay, if someone already sent a pointer and it points to somewhere and it wasn't yet received, I will be spinning here, right? Because we have to send messages one by one, right? And it's a very primitive queue. However, the moment this flips to 0, you essentially assign the new object to this. Maybe this is object 1, this is object 2. You assign it to the queue and you're done with sending, right? Here, what happens, you receive in a similar manner. You say, look, okay, I will say, I will pick up whatever the queue contains. If it contains a pointer to an object, right, I will get it in my local variable p. If it's 0, I will continue spinning here, waiting for this message to arrive. If not, yeah, well, I will make sure that I picked up the object into p like this, right? So now qptr can be 0, so this guy can send, the sender can send another message, right? Agree with this? This queue works, right? However, it's not super efficient. I mean, it's efficient for some workloads, but other workloads, it's not as ideal. So what is wrong with this queue? What do you think? Why it's not ideal? Who can tell me? There is a fair amount of spinning. So maybe you're sending messages between two processes on a single CPU, right? This is P1 and this is P2. So if P1 is not running, this sender, if P2 is not running, the sender P1 will be spinning here for quite a bit of time, right? Wasting essentially the CPU cycles. It will be waiting for P2 to wake up, get scheduled, pick up something from the queue and so on, right? The queue can have only one variable at a time. I agree. That's yet another deficiency of this queue. So ideally, you build queues which contain multiple elements. I totally agree with you, but let's concentrate on synchronization here, right? Okay, but you got the point. So you might imagine a setup in which you say, look, instead of like spinning until forever, right, we will introduce a sleep primitive, right? And we've seen those sleep and wake up primitives in the Linux kernel, but essentially sleep allows the process to go to sleep and wait until someone sends a wake up signal, right? And this way, you know, like if the queue is full and you cannot enqueue anything into the queue, you can say, look, I will be sleeping on that queue, right? And the moment someone picks up the element from the queue is also available, and then I'll be woken up, right? And if you say like, I want a queue which is kind of like a pipe, which contains not a single element, but instead maybe 512 elements, you can still run into the same case because you quickly fill in the pipe, right? And it's completely full, and you still have to wait until someone picks up at least one character from that pipe so you can add another character, right? So still spinning there is not a good idea. So it would be much better to essentially go to sleep and then be woken up later, right? Agree that it will save some CPU cycles, right? So we want to build this code something like this. You say, look, the moment we enqueue an element, we wake up the receiver. And the receiver, instead of like spinning here forever, it spins 1, sees 0, and goes to sleep, right? Does it make sense? The question is this code correct? Or something can go wrong here. It can send the wake up before sleep happens. Exactly, Dominic. And this is called a lost wake up problem, right? Let's take a look at how it may happen, right? So for example, receiver test the variable, asking is the queue contains an element. The answer is no, it's empty. Then maybe it slows down for whatever reason, maybe some other interrupt comes in, preempts it to execution, right? Meanwhile, the sender stores P on the queue, sends a wake up, right? Wake up reaches this CPU. There is no one sleeping yet, right? So it goes into nowhere. Then this guy goes to sleep, right? And it will be sleeping, waiting for wake up forever because, right? Because if this guy comes in and tries to essentially add another element to the queue, it will test the queue, it's already full, and it will spin forever, right? So this is a lost wake up problem, right? Okay, so you might think, okay, let's solve this problem with locks. Let's first acquire a lock here, right? Implementing a critical section, checking the queue, right? And then waking up someone, right? And this guy also acquires the lock, checks the queue, goes to sleep, right? And supposedly that should solve the problem. However, it's not. So do you see a problem with this code? Why is it incorrect? Exactly. So the receiver can acquire the lock and then go to sleep without releasing the acquired lock, right? Acquired lock. And this guy will be spinning here forever trying to reacquire this lock, right? And it's a deadlock. This guy will be waiting, spinning there forever. So this is not okay. So the question is, how can we fix it? Do you see a solution? We can pass the lock, this lock, we can pass it inside the sleep function and somehow release it inside the sleep function, but in such a manner that we don't break atomicity, right? Making sure that while we're releasing this lock, no one else can quickly just send a wake up and we miss it, right? Let's take a look at how we can do this. So the idea is that we acquire a lock, we pass it inside the sleep function. The intent is that sleep will release the lock for us, right? But only after we're properly put to sleep, right? Okay, so this is what xv6 is doing. It says the following. It acquires a global p-table lock first, and no wake up function will go forward because the wake up function will also try to acquire this p-table lock. After this p-table lock is acquired, this lock, which essentially is passed as an argument, is safe to be released, right? Because we know that wake up will not go forward. If wake up essentially acquires this lock before us, we will have to wait, right? And then the wake up essentially it means that wake up cannot even proceed because wake up first has to acquire the lock. So if wake up acquires this lock first and then sends a wake up, right, then it means that we will acquire this lock later and we will see this update as not zero, right? We're not going to even go to sleep, right? But which, like in this case, we acquire yet another lock first, p-table lock, preventing concurrent wake ups, right? At this point, how do we put the process to sleep? So what happens here is that we update the process field saying that we are sleeping on a channel, and it can be any weight pointer or even write any number, to be honest, right? The operating system will essentially go through all the processes which are sleeping and wake them up if this number matches, right? Then we say, look, our state is sleeping, so which means that the scheduler will not wake us up, will not run us, right? Will not attempt to schedule the process. And then we go into this cat function, which essentially will invoke switch later on, right? Remember the trick here that the switch itself requires to have the p-table lock acquired, and it will release it on the other side. When we switch from here to the scheduler like requires us to hold the p-table lock, but when the scheduler switches from the scheduler to the next process, on that pass, we will release the p-table lock. So p-table lock is a little bit magical, right? And back then, again, when we will be coming back and we will be woken up, let me take a look at, let me show you how the wake up function is working. So the wake up itself first acquires the p-table lock, making sure that it's atomic with respect to sleep, then uses this wake up function, which takes this channel argument. It goes through all the processes in a system. It's not the most efficient implementation, but fine, xv6 just does it. It checks if the p state of the process is sleeping, and if it's actually sleeping on exactly the same value, right? So maybe it's 55. Maybe this guy is sleeping on 57, that we skip it. But if it sleeps on 55, we change the state of a process to runnable. And that essentially, that's sufficient because the scheduler will eventually pick up this process and will start running it, right? Agree? So in similar, when we start, remember, I wanted to say, so we went to switch, we went to sleep. Someone later on wakes us up, changes our state to running. At some point, the scheduler picks this process, and we essentially will return to exactly this line, right? At this point, we will release the p-table lock, right? Because we, again, remember, across the context switch, the p-table lock is always held. So we release it, and we acquire this original lock as well, right? And then we exit from the function. Agree with this? There is a little bit of a business here. So go ahead, read the book and understand why these lines are not flipped here. It's a good question for the exam as well. I'll ask you maybe. I think it's explained in a book. I used to explain it as well, but we'll come back to it during the finals. But make sure that you understand that these two lines are in a correct order, right? Because it seems naively that you should first acquire lock and then release the p-table lock, right? Okay, so we are good with this. Okay, what am I doing here? we understand how sleep and wake up work. And I promised you in the very beginning of this class that at some point, we'll go back and take a look at pipes, the internal organization of a pipe in the Expo6 kernel. So the pipe itself is the following. It's a data structure which contains a log and has a buffer of a pipe size, right? So 512 bytes, right? And it's organized as a ring buffer. So the pipe itself will have two pointers. So essentially when you read something from a pipe, right? So this data which is already in a pipe, and you read these 4 elements, for example, or maybe 3 elements, you know, this n read will get updated to here, right? And essentially these elements become free, right? And when you write into the pipe, essentially you say, look, this used to be the last element, and I wrote, for example, 2 additional elements here, right? Agree? So it's kind of a ring buffer. And if this pointer catches up with this one, the pipe is full, right? And so there is like 2 conditions which you might check. So the buffer is full is when this p-write pointer points right here, right? So it's pn read plus pipe size, right? So essentially you can no longer add elements to the buffer. And the pipe is empty when p-write and p-read point to the same element, right? So, and the code of the pipe essentially is the following. So the read function, which reads data from a pipe, acquires the pipe log. It checks whether the pipe is empty, right? So if the pipe is empty, this is the empty condition here, right? It will essentially go to sleep saying, I will put this process to sleep, and I will use this address of this log as a channel, right? I will use this log, and I will use the address of this nRead pointer as a channel, right? This is the channel. It doesn't matter, it's a unique address, so we can use it like this. So at this point, the process which does pipe read goes to sleep, right? Later on, it will be woken up, we'll check the same condition, supposedly now it's false, and then you go and essentially read the byte, essentially until the pipe is empty again, you essentially copy it into the user provided buffer, which is here, right? So essentially you use this modular arithmetic here to make sure that you're circling in the buffer, right? And you're reading the pipe data into the user provided buffer character by character. So it's not the most efficient implementation, but it's not the worst one either, right? And at this point, you say, look, maybe at this point, the pipe write encountered the case when the pipe was full, and that's why some other process is sleeping on a pipe, waiting for us to pick up some data, right? So that's why we wake up everyone who can potentially wait on this pn write variable or this channel, right? And then we release the log, right? This is internal organization of a pipe, and the write function is similar, right? So essentially, I go here one by one. The write function is similar. So essentially, you check for the condition if the buffer is full, right? If it's full, then you try to wake up a reader, but yourself you go to sleep, hoping for the reader to pick up some data from a pipe. However, if it's not full, you essentially write from a user provided buffer into the pipe, right? And when you're done doing it, you try to wake up all the readers and again release the pipe log. So essentially, this is how pipes are implemented as like more sophisticated queues in the Expo6 kernel, right? Okay, so this is the end of this lecture. Next time on Monday, we're gonna take a look at the file systems, and that will be our last week, if I remember correctly. So we will have 2 lectures on file systems, right? And today I canceled my architecture class just because it's too late, and it's Thanksgiving tomorrow. So instead of the architecture class, if anyone who overlaps with operating systems and architecture, I assigned a video to watch it, right? Just a heads up. So if there are any questions, I'm ready to answer. So we'll hang out here for a sec. Otherwise, happy Thanksgiving. All good? Everyone get tired of pipes and synchronization? Useful topic. To be honest, all the code which you're going to be programming will require some kind of a working discipline. So you have to understand it well, even outside of the operating system class. But anyway, so thank you all again. Thanks for joining. See you next week.